So ISDN B-Channel protocols is the subject for tonight. I was using ISDN back in the 90s, yeah, I mean, I always knew you could select different B-channel protocols in your terminal adapter or ISDN interfaces, but I never really was fully aware of all the low-level details associated with that. Now that we are doing some retro networking implementation of ISDN, this has moved more into the focus. Also with the sort of high-level goal or final goal of implementing all of those in open source software, so we can terminate those protocols without the need of necessarily actual retro gear. Of course, we still want to use it, but maybe not always, and not always on both sides of a link. So this is basically the status of my research in those protocols. If anyone has more in-depth knowledge or I'm saying anything wrong, please feel free to correct me at any time. Yeah. So what will we cover in this talk? Well, very quick recap on the D channel and on the sort of on the overall, the big picture. And then we look at different B-channel classes and formats with all those various acronyms stated below, looking at the details, what each of those do, how they work, and so on. So why B-channel protocols? I think everyone here, or most people here, will have seen ISDN D channels every so often. Since that is what you need anyway for signaling, even for voice calls. So there is ITU-T Q921, also called LabD, the layer 2 protocol, the link layer protocol, and we have the layer 3 protocol, Q931, with its various dialects, such as 0 ISDN, EDSS1, and other national dialects for call control on layer 3. And for those, you can find any number of several, at least, open source implementations around. There's quite a bit of literature on them. And you have protocol decoders in Wireshark. So I think those are relatively well known, since that was what everyone needed to look at when debugging any kind of connectivity problems, signaling problems, and so on. And it's also what you need for a PBX, even if you only do voice where you don't have any B-channel protocol. So it's a necessity in all cases involving ISDN connectivity. Now, for ISDN B-channel protocols, well, why do they exist at all? I mean, for voice calls, it's just a bit stream, as we know, and it contains samples of audio data. So there is no protocol. And for data applications, why do we need specific protocols? I mean, basically, ISDN replaced the classic telephony system, the analog telephony system. And in that situation, we had modems to actually convert digital serial data from computers over these analog phone lines. And now that we have a digital ISDN network with the digital communication and a digital stream of data, why do we need any additional protocols, right? The main answer to that is that the serial data that you traditionally transmitted over modems is basically not just the stream of payload bytes, but also stuff like modem control signals for carrier detect, for hardware flow control, and things like that. And also different systems have different number of data bits and stop bits and parity bits enabled or not, even or odd parity, and so on. And last but not least, there are also obscure things like the break condition on serial lines that somehow you may want to replicate in a transparent way. Because when ISDN was introduced, all the existing applications for data were developed for modems before. And now ISDN sort of needed to provide the emulation of what modems is done. And Well, Wimpy says that stuff that's not transmitted over the line. Well, that's actually, we will see. We will see. I mean, with a modem, it is maybe not, but with ISDN to replicate with terminal adapters, it is, depending on what B-channel protocol you're using. So yeah, that's sort of the reason why those protocols, at least those related to transmitting data in some form over ISDN. There's of course also protocols that are more targeted, for example, for video telephony, which is H.221, which we will also cover here. So yeah, we have basically these classes of protocols. We have systems that allow us to transmit legacy data from so-called V-series applications. That's because classic modem systems were described in ITU V-series specifications. And so like V32 or so on. And these applications basically were they existed, and existing systems knew how to talk to modems, and then ISDN needed to replicate that in some way. And for this, there's basically three popular standards, or they were popular, let's say it like this. There's V.110, V.120, and X.75. We will look at those. For video telephony, the outermost layer of B-channel protocol in the stack there is a layer called H.221. And then there's other data traffic that is just doing bit synchronous HDLC or octet synchronous HDLC for applications like PPP, like the point-to-point protocol used for IP access, or also other things, but most popularly IP. So a bit about the terminology. So in the end, what we are talking about, at least for those first three protocols here, V.110, V.120, and X.75, we are talking about so-called terminal adapter, which is something that adapts the existing application that used to talk to an analog modem to ISDN. And of course, it's not a modem anymore because you don't modulate anything. It's just like formatting bits left and right. The interfaces we see in those graphs are the R interface, which is the V-series interface. You can think of it as the serial port, the RS-232 interface between the computer or terminal and the modem or terminal adapter now. And we have the S or T interface, like the S0 bus in German, and the U interface, which was called UK0 in Germany. If we look at V.110 as the first type of protocol, let's look at this reference diagram. This shows different possible configurations. So we have the ISDN network in the center. We have typically there might be lower level details like an NT and so on, but in the end, at some point, there is an ST interface, meaning a basic rate interface. And either you have terminal equipment that can directly speak ISDN, so it attaches directly to this SOT interface, or you have a legacy serial terminal or other application that uses a serial line on the R interface. And traditionally, there used to be a modem here, but now it's a terminal adapter which talks to the ST interface on the other side and to the ISDN network. And on the other side, the peers to which we are talking, we have the same situation. So we can have a TE1 talking directly to a TE1 without a terminal adapters, or we can have in the TE2 case with a terminal adapter at one end, but not at the other, or with terminal adapters on both sides. Well, yes, Wimpy, the comment, they don't have to be basic rate, but that's how it is specified this is straight from the ITU-T specs. Of course, we cover one common situation and not all potential theoretically possible situations, as otherwise it would be rather difficult to look at those diagrams. So one situation that has been specified, which I'm not really sure this has seen the light in public networks, maybe you have some ideas on that, is the idea that there could be a network-based interworking function. So let's say you have here some kind of serial terminal attaching to a terminal adapter that speaks V.120 or something like that. And it calls over ISDN an analog phone number in the analog network, and a interworking function is placed here to the national PSTN. The suggestion was made for GSM. Yes, that's for GSM, but here it says PSTN and not GSM. So I'm asking whether anyone knows about network-based interworking functions between analog modems and ISDN terminal adapters. So that I was not aware that this existed. In my world, you either did an ISDN or ISDN call, or you had an analog modem with an AB adapter or a PBX. So basically you did analog over ISDN, but then you had modems on both sides. But terminal adapter to modem with an network-based interworking function, I haven't really seen. But according to the spec, it's also permitted. Of course, it would be rather expensive for the network operator to have thousands and thousands of interworking functions. So that's probably the reason why we didn't really see that. So let's have a look more detailed about V110 as the first one. That's the one where I had my main interest, since circuit switch data in GSM is something that is on my plate to look into implementing. So V110 supports both synchronous and asynchronous serial communication on the user side, and supports a variety of different bit rates. Now let's look at the synchronous use case first. In the synchronous use case, we have here a serial interface that is a synchronous serial interface, meaning it has a clock and you have bit synchronous data. This could be an X.21 or something like that, I suppose. And you have a synchronous bit rate entering the terminal adapter here on the left-hand side, and you have two rate adaptation functions, RA1 and RA2. And those two terminal adaptation functions convert the stream to the format that is present here at the right-hand side of the terminal adapter, which is the 64 kilobit bit stream of the B-channel, going over an S/T interface. So the two rate adaptation functions, we will look at how those work in detail. In the end, that's the, yeah, okay. So we will first look at the rate adaptation function 1, which has the task of converting from whatever is the synchronous bit rate here, so any of the rates listed above here, the synchronous bit rate, and convert that to the 2 to the power of k 8 kilobits. So basically it generates an 8, 16, 32 or 64 kilobit bit stream here. And then we have rate adaptation function 2, which only adapts from those 8, 16, 32 kilobits to 64 kilobits as a second step. And we are now looking only at the RA1 function for the next couple of slides. So V110 is rather different from a lot of the other protocols that you see. It is not HDLC based. You do not have like flag octets or anything like that. Rather, it's a bitstream multiplex protocol. And in the 64 kilobit bit stream, we have 80 byte large frames. 80 bit large frames. So we have 10 bytes, and each byte has, of course, octet has 8 bits in this context. And in such an 80-bit frame, we have a framing structure with a frame synchronization sequence. So the first octet is entirely 0, and then the uppermost bit of all the following octets is 1. And this sync sequence is used by the receiver to synchronize to this bit stream and to identify where in the stream this frame structure starts. And then, so we have 8 plus 9, so 17 bits sync pattern here. And then we have other bits in the frame. That is 48 data bits. That's the user data bits, numbered D1 to D48. and we have 7 E bits, which are here. They are used to encode the frame format or rate that is used in this connection. And then we have 8 S or X bits, which are used to encode the status lines of the modem, such as carrier detect, DTR, CTS, and all of that stuff. So these bits are here. We have S, X1, S3. It's quite interesting that all the other bits you have whatever E1 to E7 or D1 to D48, but the S bits you have no S2 and you don't have S7. They just renamed them to X or something, I don't know, but S2 and S7 basically don't exist, but instead you have X bits. I'm not sure why they have such inconsistent numbering. But that's how the frame looks like. Now the question is, how are those user data bits structured in the frame itself? And that since the frame rate is constant, of course. So we have these 80-bit frames at a constant bit rate. If you remember the last diagram, so here at the output, we have either 8, 16, 32, or 64 kilobits here at the output of RA1. So we have a fixed frame rate here on to generate in the terminal adapter, and we have a lower input rate of bits from the user side. Now the question is, how do we stuff those D1 to D48 bits in order to achieve the desired user bitrate? And that is the diagrams from this slide, where we can see, for example, at the 600-bit user bitrate on the input side, adapting to an 8 kilobit intermediate rate at the output side, we basically have, 8 times repeated every bit. So the first user bit gets sent 8 times at the positions, the second user bit gets sent 8 times, and so on, and you fill it up. And at the end, we basically have transmitted 6 user bits, duplicated them a sufficient number of times, and add the frame overhead and everything to achieve the 8 kilobits per second output rate of this RA1 function. And then for other bit rates, we basically have other schemes, how those D bits are replicated to achieve the desired rate adaptation. So 600, 1200, 2400, and then n multiplied by 3600 bits. So that's most of the other modem bit rates that can be used here. And then the first 3 are only for the 8 kilobit second intermediate rate, but the other one is also possible for 16 or 32 kilobit intermediate rates. And that determines whether it's 3600 or 7200 or 14,400 bits per second, for example. What I didn't cover here in a separate slide. So the first 3 E bits here, if you remember, the generic frame structure says there is E1, E2, E3, and then up to E7. And here E1 to E3 are always fixed, and this is they actually tell you which adaptation frame format is used. So when you receive a frame, you can look at those 3 E bits, and then you know, oh, this is a 600-bit or a 1200-bit rate adaptation based on those 3 E bits. The S and X bits, as I said, they are encoded. They're used to encode flow control and other status information bits. And that's actually interesting because the specification goes as far as to tell you at which of the data bits the respective S bit is sampled in the terminal adapter. So at a given point in time, any given of those bits encodes one specific of those signals, let's say CTS or RTS, and then the bit is supposedly reflecting the state of the RTS or CTS line during a very specific bit position of the data bits. I'm not sure if anyone has implemented it with that level of precision, but at least according to the spec, even the exact sample amount for each of the handshake signals is specified. Okay, so that's basically, the RA1 for the synchronous use case. What's more commonly found in modem type applications outside of specific applications is asynchronous serial communication. So we have our normal UART, our RS-232 interface, which is commonly known from PCs and other computers. And the UART is an asynchronous interface, of course. So in this case, what happens is that the existing, like in the synchronous use case, we have RA1 and RA2, but we get an additional rate adaptation function in front, RA0, which converts from the asynchronous bits and bytes received on the R interface to a synchronous bit rate that gets fed into the RA1 function, and then it proceeds as in a synchronous use case. So it's the synchronous use case plus an additional RA0 function. And all it really does, it took me quite some time to understand that until finally it's completely simple. All it does, it is doing stop bit manipulation, which means instead of the one or whatever number of stop bits is specified in your asynchronous user rate, it just puts additional stop bits at the end. So if let's say there's one character is received here, and then there's a pause until the next character is received, then the pause is simply a sequence of stop bits in the synchronous stream. That's all there is to it. It's super simple. Nothing fancy about it. So we have the stop bit manipulation, and in the reverse direction, we remove those extraneous stop bits, and everything is fine. So it's very simple. And the bit rates supported are given here in V110. There's another table from the spec, which then shows you how this is the tolerances and which data bit numbers are supported and so on, and which is the intermediate bit rates. So let's say we want to transmit 19K2 asynchronous bit rate. This means we have well, it's actually a bad example because it's an exact match for the synchronous bit rate, which is 19,200, and the intermediate rate is 32 kilobits. And then from the 32, we go to 64 in the RA2 function, which will be covered just in a few minutes. So basically, when the asynchronous rate equals the synchronous rate, then it's easy. There is no stop bit manipulation because it's identical. But if the asynchronous rate is lower, let's say we are talking about a 14.4 kilobit transmission, then this is basically stop bit inserted up to 19.2 kilobits, and that synchronous 19.2 then goes through RA1 function. And then finally, we have RA2, the rate adaptation function 2, to go from the 8, 16, or 32 kilobits to 64 kilobits. It's actually not specified in V110, but it just points to I460, which is another ITU specification, which basically just means if we translate from an 8 kilobit to a 64 kilobit signal, we only use the least significant bit of each byte. And if we transfer from 16K to 64K, we take the 2 least significant bytes, and if we go from 32-bit to 64 kilobit, we take the 4 least significant bits of each byte, and that's it. And in case you've seen GSM before, it reminds a lot to the 16 kilobit subslots as we have in the GSM ABIS interface. But one difference here is that in V110, you cannot multiplex several different serial signals through one 64 kilobit slot, whereas in GSM that is the normal case. So you have 4 16K slots going into one 64K slots, but here we waste all the additional bits basically in this V110 spec. You cannot multiplex. Some people are typing, so maybe wait a minute. Yeah, there's a comment regarding ROP bit signaling. Well, that's an American problem, and V110 is not used or cannot be used over restricted digital, so 56 kilobit ISDN. It's not possible. Christoph also says no, there's no provision for that whatsoever. So it is only possible in a true transparent 64 kilobit time slot. which also brings us to the reason why V.120 was much more commonly used and found in the US, whereas in Europe I didn't really know many BBSs, for example, offering V.120 because it was not commonly used here. Okay, so there's something else we have the rate adaptation function and so on. So there is the synchronization of the entry and exit into this terminal adaptation. And this is a timeline from top to bottom in this diagram. So we have the two users using their terminal adapters to establish the B-channel. And this just gives a diagram of which of the status control lines is set in which way and then detected by the other side and responded in a certain way to make sure that they both have frame alignment and they both start at the same time. And to make sure, let's say, for example, the DTR signal is only asserted once everything is fully set up here and frames are aligned and everything is working. So these strange, if you're not familiar with ITU specs, these 105, 107, 106, 109, these are the circuit numbers from from ITU specifications for serial circuits. They basically, this is your RTS, CTS, DSR, DTR, CD, and so on from the RS-232. I created a table in the Osmocom wiki, and I actually print those specs and manually always write the, to me, much more known naming that we know from serial ports and modems, rather than those strange circuit numbers next to it. I think 106 was CTS, but I think that's the only one that I remember off my head. Yeah, then V.110 also has completely different rate adaptation functions for synchronous rates of 48 kilobits and 56 kilobits, but that is again user bit rates, and it still needs a transparent 64 kilobit B-channel on the ISDN side to work. There is also some method for in-band parameter exchange. I didn't really look into this, and there is some facility for network independent clocking, meaning that it supports synchronous bit rates that are not synchronized to the same clock that the ISDN. So let's assume you have some equipment doing synchronous communications, synchronous serial communications, but it has its own clock at the same rate as ISDN, but not locked or synchronized to ISDN. And that's basically some elastic buffer thingy that they put in, and I think some signaling between the two ends, whether to drop a bit or to insert a bit to make sure there are no underruns or overruns. Yeah, so that's V110. Yeah, a slide about the interworking function. We had this discussion before. I didn't really see that in real-world networks. The only V.110 usage that I ever encountered, and of course, as I said, I'm not the expert, but I've only seen it in the context of GSM in a popular way. And GSM has this facility called circuit switch data, which is basically a V.110 derivative. So the V.110 frames are modified in some ways, and then the modified V.110 frames are sent over GSM radio channels with specific new circuit switch data specific convolutional coding and so on, and interleaving. And there then is a GSM specific interworking function between the GSM network and the ISDN network. So on the GSM side, we have those modified V110 frames, and on the ISDN side, we have the normal plain V110 frames. And you could, and I think you can still, at least in some cases, establish circuit switch data between ISDN and GSM exactly that way. So, and it was pretty standard in the days before a packet switched mobile service. So in the circuit switch data days before GPRS, it was common that you would dial from a GSM data modem to an ISDN terminal adapter at the other end, or vice versa. Okay, so that's for V.110, and now we go to something completely different, which is the most simple and most basic HDLC-based B-channel protocol, which is HDLC with synchronous PPP specified in the two IETF RFCs given here. It's basically just using the flag octet mechanism of HDLC to delineate the start and the end of the frames in the bit stream of the B channel. And then in between we have an address octet, which is always 0xFF, and a control octet, which is always 0x03. And then a 16-bit frame check sequence and a flag octet at the end, which I didn't really mention here because it can be the same as the start octet of the next frame. And there's an optional compression mechanism specified, which suppresses the address and control octets on transmit. So basically, we end up with a flag octet, the PPP frame, and the frame check sequence at the end. And that's the most simple HDLC-based B-channel protocols that you can imagine. It's also why I'm discussing this right here. So in the family of protocols that I'm speaking about now, and X.75 and V.120 in the next chapters of this talk, they all have this idea that you have the serial bit stream and you have flag octets with a specific pattern. And if this is identified in the serial bit stream, it delineates the start of a frame. And then you have any number of octets in between and terminate with a CRC and another octet at the end. Also, what happens is some bit stuffing on in between the start and the end flag octets, to make sure the 7E pattern only occurs in this situation. So if you have 7E as a payload in your frame, then there is some insertion and or removal of bits on the receiver side to make sure that this pattern really only happens at the start and the end of the frame. So that was used quite a bit, particularly for, let's say, if you have Linux computers with a ISDN terminal adapter and you would do internet access, then sync PPP over HDLC was the most efficient way of and with the least overhead to get internet over ISDN. X.75 is another B-channel protocol that also uses HDLC-based approach. So we again have 7E as a flag octet. We have an address octet and a control field, variable length information field optionally, and the frame check sequence. And X.75 is really like all of those protocols. If you've seen one, you've seen them all. It started with, I think, IBM SDLC, then it became HDLC, then LabD, LabB, LabBM, LabDM, LabSat, and all of these protocols, they all look the same with minor differences in some parameters. Sorry, that's actually, that frame is at the wrong location. Sorry, that slide is at the wrong location in the slide deck. So let's jump to X.75 actually. Apologies, before going back to V.120. So X.75 actually predates ISDN. It was specified as part of the PSPDNs, the packet switched public data networks, also known commonly as X.25 networks, even though that's not correct, since X.25 only specifies the user interface, meaning the interface between you as the user and the network. So it's a bit like calling the ISDN network the, I don't know, the BRI or S network. It would be the same mistake. You call the entire network based on the interface it provides towards the user. So in X.25 network, the only or PSPDN network, the only interface specified was X.25 between the user and the network, and then inside the network itself, this is multiple networks here. But inside the network itself, it was left as an implementation option. So any operator could implement whatever they want inside the network, but then to the next user external to the network, it would again be X.25. And ITU specified X.75 as an interface between the operators. Excuse me for a second. So, sorry for that. So we have, let's say, if you have a German DATEX-P user, which was the German packet switched network, and a French Transpac or US Telenet subscriber, and they would exchange data over these networks. Supposedly there was X.75 between the German network and the other networks, and that's the origin of this protocol. So it goes back to the early 70s. Much further than ISDN. And then when ISDN came around, they extended this protocol or adopted it extend is actually the wrong word. They used a subset of X.75 for ISDN B-channels, specifically the so-called X.75 SLP single link protocol. And the ITU's recommendation T.70 contains the specific rules how X.75 then was used in ISDN. So it basically contains all the parameters and restrictions and constraints of X.75 as it is used over B channels. So how do the frames actually look like? As I said, it's like all of these HDLC-derived protocols. We have the flag octet, we have an address octet, a control octet, then an optional. So this is the short frame situation where there's no information part. It's only address control. And this on the bottom side shows the long frame format. So we have a flag, address, control, then n number of information octets as the I field, the information field, and then a 16-bit frame check sequence and a flag octet at the end again. So the only difference between those two parts is whether the the information part exists or not. That's the only difference between those two. And if we look at the kind of commands that exist, there can be, excuse me again, I have this black cost. So we have the address field. We will get to that, what kind of address fields are used in this context. And we have the control field, and the control field can look like this. So we either have an information transfer frame with a send and receive sequence number of 3 bits each included. And then we have other frames for indicating receiver ready and rejecting frames and so on. We have the SABM command, which is for initiating the connection. It's basically your SYN packet if you think of TCP, and the disconnect, which is your FIN packet, and some other acknowledgements and so on frames. So these are all the frames that exist in X.75. And note, there is no UI frame. So from GSM, for example, we know, and I think also in LabD on ISDN, I think, there are UI frames, unnumbered information frames, which means you can have information frames that are not acknowledged and not retransmitted and so on, basically UDP-style communication. But in X.75, that is not present. The only frame that carries user information is the I frame, and the I frame then is for confirmed and acknowledged transmission. So what kind of addresses do we have? There's really only 2 addresses used in X.75 on the single link, which is the address A coded as 3 and the address B coded as 1. You can see that here again. Note that the bit order in those X.75 and other related specs is always the wrong way around, at least from where I've been growing up. So it's always the least significant bit is written here and the most significant bit at the end. So this is actually a 3 and this is a 1 if you look at it in decimal notation. So, and yeah, the structure is as indicated in this figure at the right bottom side. So we always have the calling side and the called side. And if the calling side sends a command to the called side, it uses B as the address. And if the B side responds to that, it also uses B as the address. On the other hand side, if the B side sends a command to the A side, it uses A as the address, and the responses to that use A as an address again. Yeah, that's all there is to the addresses in those X.75 frames. So that's it for X.75. Note again that it is always using acknowledged mode. And now we get to V.120, which is also a protocol for a terminal adaptation. If we again compare the two systems that we've seen so far, we have V.110 as using this kind of bitstream multiplex with its own frame structure and so on. V.110 has the ability of replicating modem status lines and of really emulating a modem with all of its control signals on its RS-232 interface. X.75 is not. Right? In X.75, there is no notion of having any indication of flow control signals or carrier detect signals or anything like that. That's completely non-existent. It is not a protocol that is possible. And V.120 now combines a bit of both worlds. So V.120 is a protocol for terminal adaptation of a serial port of a UART. But internally, it doesn't use this kind of bitstream and rate adaptation approach of V.110, but it uses an HDLC-based frame format for transmitting those frames over the ISDN B-Channel. And unlike V.110, it supports the operation over both unrestricted 64 kilobit B channels and also those restricted 56 kilobit channels, which made it popular in the US, where 56 kilobit user channels were common. So the least significant bit is simply not used in this case, and that's it. Also, unlike V.110, it supports multiplexing multiple low bitrate serial streams as logical links over one B channel. I'm not sure any terminal adapters actually implemented it, but at least in the spec, it's possible to do so, which of course makes sense. If you had such applications, why would you have one dedicated B channel for every 2400 BPS link? You could just aggregate them and multiplex them. Also, since it's not, let's say, bit-oriented transmission, but works with frames, it can implement compression of the data. Since data is buffered on both sides anyway, you can actually go and compress that data before transmitting it over ISDN. Though, of course, I mean, if you're transmitting 9600 BPS low bitrate signal, there's not really much need to compress it if you have a 64 kilobit channel anyway. But I think this makes more sense in the context of having multiple logical links inside the B channel. So it has an entire protocol stack inside the B channel. So we have the data link core frame at the bottom, which has again a flag octet, the F at the beginning. It has an A, the address field. Then we have the data core information field. That's we will look at that. That's basically what is part of the next protocol layer up there. And again, a 16-bit check sequence and another flag octet at the end of the header. And inside this data link core frame, we have the data link control field, which has the control frame and the information field. And in the information field, we then have another type of frame, the terminal adaptation frame, which has, again, its own header. It has a couple of different modes it supports to transmit. There is the protocol-sensitive asynchronous mode, the protocol-sensitive synchronous mode, and the bit-transparent mode. And in the protocol-sensitive asynchronous mode, it uses iframes and asynchronous balanced mode, meaning that we have the data link layer. This HDLC derivative is actually sending sequence numbers, and if frames don't get transmitted, or if frames don't get acknowledged by the receiver, for example, because the receiver is busy in some way, then the receiver would send a receiver not ready frames, which basically blocks the transmitter from sending more data. So you have a way to do flow control by using this mechanism. The other way is to do it unacknowledged, in unacknowledged mode with UI frames. There is a specific RR bit in the control information, in the control state information octet, that is this guy here at this protocol level, which would then indicate the receiver would indicate to the transmitter whether it is ready to receive more data or not. And this basically means that the receiver, let's say it uses RTS-CTS handshake, it would set the respective handshake line, and that would get encoded either in the RR bit or would trigger the RNR frame transmission, go all the way to the other side, so the other side stops sending more data. Yeah, and then the other two modes, there is no flow control possible. It's only possible in this protocol-sensitive asynchronous mode. Yeah, that was the V.120 chapter. So with that, we've really covered those modes that I wanted to talk about. For data transmission, for basically transmitting modem data, in quotes, serial data over ISDN B-channels. And the last and final candidate in our list of B-channel protocols is the H.221. Which is the multiplex system that is used, the lowest layer in the video call system used on ISDN. So I think it is the H.320. I'm not entirely sure about that, like the overall system description, how video calls work over ISDN. And the lowest protocol layer part of that inside the B channel is called H.221. It's a bitstream TDMA system, so it's much more like V.110 or like an E1 multi-frame structure. You will see a lot of analogies there if you're familiar with either of those. And it is not something like an HDLC-based bearer like X.75 or V.120. However, it is much more complex than V.110. Since we don't just have frames, but we also have multiple multi-frames, meaning we have a higher order time multiplex system, and the frames are much larger. So in V.110, we were talking about frames that have 80 bits. Here, a frame has 80 octets, so 8 times the size for the frame. And the multi-frame then is 16 frames, so a total of 1,280 octets. The frame structure is given here on the left-hand side. So we have the 8 bits in the horizontal side, and we have the octets in the vertical side here. And we can basically see that the sub-channels are divided by bits. So the bits 1 to 7 of each byte are each forming one sub-channel. So basically instead of having one 64 kilobit channel, we split into 8 kilobit channels here. So we have 7 sub-channels of 8 kilobits each, plus the 8th sub-channel is then used for framing and some related signaling. So that is how the frame format looks like. And the frame alignment signal, the FAS at the beginning here, so at the first at the 8th bit of the first 8, each of the 8th bit of each of the first 8 octets forms the frame alignment signal. And that is, as the name implies, is how frame synchronization is established again by the receiver from this. Then we have the BAS, the bitrate allocation signal, which encodes sort of how these sub-channels and so on are structured. And then we have ECS, that's an optional channel for encryption control. I've never looked at how this encryption of video calls on ISDN was specified. And we have an 8th sub-channel, which is either very low bit rate, since we have always these other channels on that bit shared with the sub-channel number 8, so that's a much lower bit rate channel. But if ECS, the encryption control signal, is not used, it actually gets some more bits, since ECS is not there and the sub-channel 8 gets larger. So that's the frame structure of H.221. And then from that frame structure, we go to the multi-frame structure. But before we do that, sorry, the frame alignment signal, how it looks like. So here again, we have all the different bits of our bytes in the ISDN B-channel. And now we are only looking at the control channel, which is basically this highest bit here, bit number 8. And if we look at this only these bits, and we plot them basically from 1 to 80, and we rotate them by 90 degrees and only looking at the first 8, and we see, well, yeah, here this is the pattern of the frame alignment signal that we see in this frame structure in the even frames. And in the odd frames, we have some other bits, the A, E, and C bits. And if we plot this for the entire multi-frame, again, these are only the bits of the service channel, meaning the last or highest order bit, whatever you want to call it, the rightmost column of the frames before. So, and here the frames. So we have 16 frames, and we only look at the first 8 bits of the service channel, which is the 8th bit in that structure. So every even, so at 0, 2, 4, and so on, we have the frame alignment signal here that's static. And on the odd numbers, we have other bits here, as said, the A, E, and C bits. We also have some other bits here we can see in the bit number 1, like N1, N2, and so on. The N number specifies the multi-frame number, so you can actually, you get not just a multi-frame consisting of 16 frames, but then successive multi-frames have different numbers. So we have a number here indicating which multi-frame number is, sorry for that, is used. And we have C bits. This is a CRC4 bits. That's why I'm saying it reminds me a lot of E1, because in E1 also we have this time slot 0 with CRC and A bit for alarm and with frame alignment sequence and all of these things. So A bits here, they are basically used to communicate to the peer whether or not frame alignment has been established. So if we ourselves are one endpoint, we are receiving some data from the peer, and if in that data we have established frame alignment, so we have recognized this frame alignment sequence and everything makes sense, and we have locked onto this signal, then we signal that there is no alarm in the A bits. But if we don't, or if we lose alignment, then we signal this to the peer, so he knows that we somehow don't receive correctly anymore what he's sending in terms of the framing. Yeah, so that's how this H.221 looks like, and that's sort of where the presentation ends in terms of the theoretical background on those different B-channel protocols. I have written a bit of code for V.110 decoding and also for the HDLC decoding of V.120 and X.75, and we can look at some real data. But before we do that, maybe now is a good point to take a break and ask for some questions if there are any. Thanks. Yeah. Did we lose alignment? Thanks, Christian. Thanks for that. It's if you're not familiar with TDMA stuff and so on, it's probably very alien, but yeah. nevertheless, I hope we can use this also when we implement more of this in the future, and we have some reference to go to. But yeah, any questions or comments?
I have the impression that in the documentation for the ELSA ISDN modems, and they aren't really modems, right? There is a special X.75 mode documented used for PTX. Do you have any idea of what the difference is?
Yeah, it's an additional layer on top of X.75. It's called T.70, I think it is. So as far as I know, basically it means it's the X.75 frames, and in the X.75, it's not the actual user data, but there's another layer on top. Yeah.
I'm asking because when I did my display tell experiments and PTX over ISDN, if the ELSA modem I was using on the other side was in the wrong mode, the display tell got hung up on something and rebooted. And if it was in that T.70 mode or something, then it went through.
Yeah, that would make a lot of sense indeed. Yeah, and it's typically in the terminal adapter ISDN modem, as you said, the terminal adapter, you have some AT commands to set the B-channel mode, and you can switch typically at least X.75 and V.120. The most popular ones, V.110. I think not all of them implemented, and then some have this PTX specific mode. Yes. Which is this additional layer on top. Yeah. So yeah, now as I said, we can look a bit at the code that I wrote. Well, not at the code, but at the results, I would say. So as some of you may know, I wrote this Osmo ISDN tab some months ago, which we use in the Octoy network to record ISDN calls, to raw recordings of the B channels. And now on those recordings, I can run tools to try to decode them. So I have files. We can try to open one of them. V.110, whatever. Let's open this. So this is a raw recording. Initially, there's some static pattern. That's before I think that's before the terminal adapter on one side actually starts to do something. Then we get all FF. I think this is specified in V.110 that you get all 1 bits. And then we start those frames. And we can see a regular pattern with this 00 basically happening here. And if we count the bytes, this is like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 bytes. Yeah, and then it starts again. So this is our 10-byte V.110 frame. So this is how this looks like. And this, of course, continues now for a very long time. And I wrote some library code that is part of a new libosmo ISDN that's coming up, which can decode this. So if I run this through the decoder, I'm actually getting, so what I used as a test here is I copy and pasted the wiki page on ISDN B-Channel protocols. I copy and pasted them on one ELSA ISDN terminal adapter and took the B-channel recording. So if we decode this V.110 here now, we actually get the Osmocom wiki page on this subject as a decode out from that binary data that we saw just in the hex dump. So the frame synchronizer we used to find the V.110 frames is the same existing synchronizer that we already had for ABIS frames in GSM. So that could be recycled just by adding the frame sync sequence for V.110. And for the frames, there's then some code. We can probably quickly open it. V.110C. So it's basically just it's a very low efficient and very primitive and simple implementation, which basically it's super inefficient, but it's very easy to compare with the specs what is happening. So performance was not a goal here initially. You can always write a more optimized version later. So we have this idea of a decoded frame, which is a C structure. Which basically contains D bits, E bits, S bits, and X bits as a separate arrays. And U bit T is just a type def, meaning we have unpacked bits, meaning we have 1 bit per byte. So we can operate in a very easy way from C without doing bit shifting and all of that stuff in all of the code. But as said, of course, it's super inefficient, but it works. So yeah, we have the encoders and decoders for those various frame formats. So if you remember, there was one where the bit was always repeated 8 times, our 600 bit per second signal, where all the data bits get multiplied by 8, and this is the mem set for that. So we basically set that that bit 6 times in the D bit section and so on. So yeah, that's the code for that. And I also have an HDLC decoder. We already had HDLC in libosmo core, so that is not really. Let me just increase the font size a bit. Yeah, so I'm using a V.120 recording here, for example, and decode that through the HDLC decoder, and we get hex dumps of the HDLC frames in there. Let's maybe start from the beginning. So we see here the frames. The FCS is already stripped, and the flag octets are stripped. So we are seeing only the address control octets here. I don't recall in V.110 what this now means exactly. I cannot tell you off my head, but we can already see that the addresses in V.120, so this is one frame, it's just broken around. So maybe this like this, it's easier to see where a new frame starts. So that's one frame. So we see the first octet is address, and we see A and 8 always in the address here. So we see these are the addresses that are used in V.120. That's also, I think, a very good way to identify which of the B-channel protocols it is if you wanted to do a brute force detection or something like that. And if we compare that with an X.75 trace, it looks like this. And here we see it's 03 and 01, the address octet, always the first frame of the first octet of each frame. As you remember, that was the addresses A and B in the X.75 specification, or in the X.75 specification. And here we have basically address, control, and then the information part of the frame. And here we only have address and control. The next steps would be to wrap this into GSM tabs so we can send it over UDP and then have Wireshark decoders. I think for V.120 it already exists, and then we can get meaningful decodes of those messages going back and forth between the two sides in such a data core. But that hasn't been implemented yet. It's only that part here. Once this is in the library proper, it's just in a branch right now. This could become part of Osmo ISDN tab. And Osmo ISDN tab, instead of doing raw recordings, or in addition to doing raw recordings, it could try to do some heuristics, whether this looks like X.75 or V.120 or whatnot, or whether it looks like HDLC based protocol or something else, and then do the decoding and feed that over GSM tab to Wireshark or something else. Yeah, and that's it. I don't have anything else to show at this point. In case somebody wants to play with it, there is the LaForge libosmo ISDN branch in libosmo core that contains the code and these tools.